All right, everyone, let's go ahead and make this. I actually found out that I have 30 minutes. I practiced for 20 minutes. Let's see how quick we can get to lunch, everybody. Okay. So generators, show of hands. How many people have ever written a generator function? That's actually better than I expected it to be. How many of you have done more than like 10 of them? Okay, yeah, that's about what I expected, right? So have any of you used them for a purpose other than building an iterator? Okay, these are my people right here. So this talk is going to be for everyone else to learn why generators are cool for more than just iterators. I'm going to blow your mind. So borrowed this from Pamela Fox. For those of you who don't know her, she's got some great content about iterators in the first place. You can see here that generator, is a type of iterator. That is true. And it uses yield. That is true. But there's actually a bunch of not the best documented APIs in the world around generators that completely don't even fit into the iterator ecosystem effectively. It still uses some of the same surface area, but your for-ins no longer apply once you kind of enter some of this world. So let's go through there and kind of talk through how we can kind of go from iterators to understanding these kind of more powerful ways of using generators. I'll skip that part. So this is an iterator. And range is the first iterator that anybody is ever going to probably use when they start using Python in the first place. And it takes in either just a max or a minute a max or a minute a max and a step. Let's say that I want to, instead of passing a step, I want to call a lambda. So I can go through there and kind of customize exactly what I'm going to do there. So I'm going to build my own custom range function. Let's use a generator to do that. This is one of the ways that we would typically go and start playing with generators as well. So in this case, really simple, taking a lambda, going to call that lambda to figure out what my step is. And the key part here to look at is I'm going to yield that. And I've got a while loop that will end as soon as my start moves past my end. Here's what the actual output looks like. You can see here that I get a 1, a 3, a 5, a 7, and a 9. Exactly what I expect, right? Nothing too magical. But the key thing here is that this function is actually returning effectively multiple results. It's yielding multiple results while that function is still alive. Normally, functions take in an input, they run and produce a single output and end. Generators generate multiple outputs. We can get fancier with this. You can see that I can do wild things inside of my lambda. So this was just, I confirmed that 2 still worked. This was showing that I can go through there and do something fancier with doing a power function inside of my iterator now. What if I don't want to set an end value, right? Step function, the current range one basically requires that it's going to end at some point. But what if I just always want a stream of incrementing numbers for forever? Well, let's go through there and allow me to set end to none. And let's see what happens. In this case, I've got this print statement at the end of my generator. And I'm going to see whether that ever is called. So I'm going to go run that. And I can run that all the way to 1,000. It's not called. I can run it all the way to 1,000,000. It is not called, right? That generator will just keep on spinning forever. And that's a good thing. If I need a function that returns results forever, generator is perfect for that purpose. But, I feel a little bit bad, right? This function, this print statement sitting there, kind of existential. This function, even though it's a generator function, it can never die. What if we did want to give it sweet relief? And that is where you start getting into some of the interesting signals that are happening with exceptions inside of generators. So you can trigger a generator exit exception and handle that properly within the generator itself. And this will now gracefully handle the generator closing. What's nice about this is let's say that I had a database iterator that I was doing here and I needed to clean up the database connection before the iterator was done. This is a perfect place to be going through there and doing some of your cleanup tasks. So let's look at how this works. And you can see here, I run this, and there's this new line that I'm calling here, where instead of going through there and doing an emergency break effectively when I get past that number, I'm now calling close, and now my generator is nice, it's happy, it's closed. If I try to go through there and call into it again, I'm going to be getting an exception that basically says that there's no more results. So that's the very first kind of, this API still works with iterators. I'm able to use this within for-in, You might not always need this, but if you did have a never-ending iterator, this is a useful method to use. Let's look at something that doesn't work within for-in. Let's look at a pattern where I can actually pass results back into the generator, as well as getting results back in. It's nice that I can go through there and pass input once to a function, if I'm going to only get one output. But if I'm going to get many outputs, wouldn't it be nice if I could give many inputs as well? Generators also have a solution for that. So what you can see here is that on the left-hand side of the yield, I'm able to actually have a value assignment. This gets into a fun scenario where you do need to what's oftentimes called prime the generator, because you can't send anything to it until it's effectively listening for you to send something. So you need to prime it with the next call. But from there on, in my while loop, I'm able to go through there and use this send. And what this is now doing is I'm now able to do that same pattern of being able to increment, random values to my step function without needing to pass a lambda in there. I can do whatever logic I want to. I don't need to one time define that as a lambda and hope that that suffices. I could completely change exactly what my step is every single time, no matter what. And you can see here that I get that same kind of step function approach with just a very simple passing in the value back to itself. It's doubling itself every time it's called in this little sample here. So that's a blast through some of the things you may or may not have known about generators. Let's talk about one of the cool things you can do with this. Anyone here contributed to Async IO? Okay, I'm getting down to the very nitty-bitty pieces here. Using Async IO, but I hope more people have their hands raised if I ask that. Contributing to, or how about like Tornado or any of the Async IO like frameworks? Yeah. So generators oftentimes get kind of left to this group of people primarily because they can actually be used for management of coroutines and things along those lines. Now, we have Async IO now. You shouldn't be building your own Tornado framework. You should be using Async IO. And in fact, even for some of the scenario that we're talking about here, there'll be another talk later by Temporal that talks about using Async IO for doing some of these tasks. So even then, you should consider whether or not you actually want to go build your own orchestrator. But let's say that you wanted to build an orchestrator. Generators is actually a perfect function to handle that. And we'll talk a couple of things that we want from an orchestrator. So with orchestrations, failures are inevitable. Anything that's going to be taking multiple steps, each of those steps has some percentage chance of failing. And as the numbers get larger, in terms of number of steps, and as the numbers get larger in terms of the time those steps take, and as numbers get larger in terms of the volume that they take, things will fail. At Microsoft, this is a constant problem because we run things at very high scale. We keep on adding complexity to workflows and stuff like that, and inevitably, the database software is working the way we expected it to. It's like the management plane that ends up having some issue because we didn't think through what it meant to add this extra step to that workflow and this error handling step in that workflow. So there's a bunch of frameworks people have built in throughout their time. I'll show you an example of kind of how this gets used in one of those frameworks that we've built. But the key thing that we need to be thinking about is that we want to break up long tasks into kind of the smallest chunk that is reasonable, which is ambiguous, but there's still a problem there. What is reasonable? What's the smallest chunk? There's a trade-off there. You can get into some fun queuing theory problems there as well. If you guys know what Erlang is, that programming language, there's also a unit called Erlang in queuing theory, which is just an abstract unit for something queued to go and do. It's a very fun space if you want to get nerdy about queue theory. The other thing you want to be thinking about is as you complete jobs successfully, you need to be thinking about checkpointing that state. So that way, if for some reason there's an entire system crash of some kind on the node that's working on that, you're able to go and resume where you were without having to repeat much or any work at all. So let's look at how we can use generators to actually solve both of those key points. So this looks like a very simple orchestration, but this orchestration causes live-side issues everywhere, all the time. I can guarantee you that so many of the issues that people have out there is effectively something along these lines where I've got one task that runs, then I need to parallelly wait for two tasks, and then another task that runs with the dependencies of those things. It looks simple here as a flowchart. It can be very difficult to actually make this run with 0% error, which is kind of what's needed if you're building these things for mission critical systems. So a naive way that I could build this is I've got a flaky activity that I've just kind of artificially generated about a 1% error rate, depending on how much you believe math, the out-of-the-box rand function for doing that. And then I'm going to be calling that, building that kind of orchestration here, where I've got, A feeding into B and C, and then B and C feed into D, and then I'm returning D. So that's the pattern that I want. I've got a little main function here that's going to go through there and plumb that, where I'm going to go through there and run this 1,000 times, track my failures, and print out some stats. So we run that, and you can see that I get 40 out of 1,000 failures. I would expect a 1% failure rate, right? My function fails 1% of the time. I'd expect 1%. Well, I call it 4 times. So simple statistics, I end up with that 4%. That's really high, and that's unfortunate. As I add more work to that orchestration, that number is going to only go up. That's a problem. We can't have, as our workflows get more complicated, they get less successful. That's mission critical. We rely upon these things working better as they get more users on them. So let's break up the task, and we're going to isolate failures from impacting the other tasks. To do that, we're going to go through there and just use a very simple wrapper. I've called this a durable activity. And what this is doing is, rather than immediately calling the activity, I'm going to basically queue up that activity to be called by something else. And in the orchestrator, what I'm going to be doing is I'm going to be, yielding basically these calls. This can look a lot like if you're building like tasks or something, or waitables and things like that. This is a very similar kind of concept. I'm going to basically be saying like, hey, I need this to be done. And you're kind of, returning a promise, yielding a promise to be used there. A promise from a promise theory perspective. I promise I'm trying not to leak JavaScript stuff in here. Promise theory is itself an interesting space to look at in this space. So then I'm going to go through there and I'm going to also do the same thing for my orchestrator. So I'm going to have a durable orchestrator that when issues happen within that orchestration, I'm going to go through there and handle those individual failures, retry them as many times as it takes. In this case, you should have runaway things, because if it's always going to fail, you want to eventually give up. But in this case, I'm going to assume it eventually completes. And then this is going to be calling my orchestrator and kind of pumping my orchestrator for me. And now let's run this at a much higher number, right? Because we've gotten more workload on our system now. We want to go through there and actually see those number of errors stabilize. And ideally, we never actually see a single workflow fail. Even if we have exceptions that happen, because failures happen, we don't want any single failure to result in a total failure of a workflow. So we run this 1,000,000 times, and or 100,000, not reading numbers well. You can see that we actually had 0 total failures. So we went from 4% total failures to 0% total failures. And for exceptions, we actually see that we only had 1% of exceptions. We're back down to effectively the base exception rate of a single activity. So that's the magic of statistics and how those things go together. By not having to ever retry the entire workload, I'm actually able to save on overall executions in the first place. So you kind of get into this beautiful thing where you do less work, and so you get less failures. If you always retry more failures, you end up with more and more failures. It can end up being this vicious cycle. You want to always isolate failures so that way it doesn't revolve in this kind of big escalating fashion. So this is all great, right? But if I were to unplug the server that this is running on while in the middle of it running, I would still have to rerun the entire orchestration in the first place. That's still a total failure, right? We didn't emulate those kinds of total failures here. Let's go through there and simulate what would happen. Let's go through there and harden this orchestration so that way the state itself is no longer bound up in just the stack call inside of the generator itself, and actually have that so I can go through there and replay that state whenever I need to, so that way I can handle if the orchestrator fails. So in this case, I've added this new, this is a very simplistic thing. You should build something more sophisticated than this, but very simple. I basically have a call stack, and this call count is really a pointer to where I am in the stack at any given moment. All I'm doing in the durable activity is I'm just logging that I created call counts in the first place. And then my durable orchestrator has gotten much more complicated. And in fact, I couldn't use the out-of-the-box NB convert reveal.js. I had to go through there and fiddle with HTML to get this screen to fit because it's longer. But the important part here is that I'm now going through there and taking the results that I get from those activity calls, and I'm putting them into my call stack. And then here I've got this kind of kill switch to go through there and simulate failure, so that way I don't have to unplug my laptop and break up the presentation for you all. So this is going to, at a certain call count, trigger a single failure, and then the next time it goes around, it'll succeed. So I'm not doing statistical failures here, I'm doing deterministic failures just to show how that works. So let's go through there, and you can see here that the flaky activity itself hasn't changed. I actually changed the function around a little bit, so I now pass the function to the durable activity, so I can do this for arbitrary durable activities. Not a super big change, but that makes it kind of nice because I can use this for arbitrary functions now. And then if we go through there and we run this, you can see that I've got one where we're never going to fail because call count 0. When we fail at 1, 2, and 3, and you can see that for the first one, it doesn't fail. For the second one, we fail on the first one, and we immediately get 1 and 30 back. That matches. For this 2 failure, we can see that we get 147, 269, and then for the last one, all these pieces here. These random numbers are being generated for these things, so that's why they don't look the same across them. But for each single workflow where there was a failure, we can see that it's actually remembering the state of that when it reruns the orchestrator. So now, the state of any given activity that was ran in the past is durable. And so if it's a somewhat non-deterministic outcome, but I don't want to have that non-determinism repeated within the system, I now have a deterministic kind of result from a non-deterministic input, which all the time that happens, right? If you had some other data written to that database, you don't want, when that activity runs again, to maybe have those changes affect the rest of the workflow that could completely change the rest of the workflow. You want determinism in any kind of orchestration to prevent those types of failures. So 20 minutes, actually pretty close. I managed to go through there and show you how close and quick it is to go through there and use generators to do these types of things. Generators, exist in a couple of different languages. Python has some really cool features in it, like yield from is a relatively unique feature that makes it really easy to stitch together generators. And what's really nice there is it's more than just syntactic sugar around for in. It's actually passing signal to the underlying generator itself. If you work in the space, that's an incredibly handy feature to be able to go through there and have the signals pass automatically. Otherwise, it's a ton of code that you've got to write every time correctly. Otherwise, it will break. So it's really nice to have some of those features inside of Python itself. I think one of the things that we probably want to improve in the Python community is that this stuff is relatively poorly documented in official documentation. And in fact, every time I need to go back and read the PEP standards where they were introduced, that's still the best documentation that exists for all of these things. So if you're interested in learning more about generators in Python, encourage you to go look up those PEP standards and some of that initial documentation. And I'm certainly thinking I should probably put my money where my mouth is and actually go through there and do some of those contributions back myself, because I would love to see more generators used in more creative places inside of Python. Now, this is a sponsored talk, so we paid to have you guys be forced to listen to me, so I'm going to go through there and do my little bit of corporate shilling here. The way that, the reason why I decided to talk about this is that I actually built this out for Azure Functions a good number of years ago now, actually. It's been a while. Durable Functions is built on this Durable Task Framework, which is a .NET framework, but Azure Functions obviously works across many different languages, and so we were trying to get the Durable Task Framework stuff, which works around tasks in .NET, to work on any arbitrary language that has something that I can go through there and kind of be able to define tasks and serialize those things, possibly even have those tasks coordinated across languages, which is really cool because we're kind of serializing the state of those asks and things along those lines. And we ended up on generators as the perfect fit for doing that at the time. There's obviously Async IO that exists now, and again, call out, please attend the temporal talk. They talk about how they're using Async IO custom to go through there and address the same problem while still keeping the async await syntax. So that's the evolution of this if you wanted to keep your async kind of pattern. I still like the generator in yield because it kind of helps me mentally break async in an orchestrator, which you want to have behave differently from async in an activity where it can fail and I'm fine with it. But it's still very interesting. So what you see here is that I've got my same orchestrator that I was showing you guys before in the slides. And I've got my same kind of activity function that goes through here and fails. And then here I've just got a little HTTP endpoint that I'm defining on the function that allows me to go through there and query it for a different status and things along those lines. I've got this running, and hopefully it will actually still be running here with internet. Nope, it's not very happy. This is the problem with live demos here. Let's see if it works. The Azure Functions devs are probably here somewhere. Panic. Yeah, there we go. Just keeping their fingers crossed that everything starts up. Okay, we're cool. Started up without failures. We're fine, folks. So what I just did there is that I kicked off the orchestration. That's an asynchronous task, right? So we're going to kick off the response, and what comes back on that response is actually a bunch of status endpoints, restart endpoints, things like that I can use to manipulate that durable task. So I don't need to build all the stuff that I just walked you guys through and things like that. I get this out of the box with the framework on top of durable functions. And then that's going to return to me the status URI. And so I can go through there and hit that status URI. And what I see is that the final number that got returned from that orchestration, that D result, was 232. I can see that I printed that out here in the logs. And that's also available as the output on this API. Obviously, you can also have that output, written to external systems and stuff like that. This is a trivial example of trying to add up random numbers, to keep it simple. But it's very nice because if anyone has tried to build async APIs, much less, kind of durable orchestration in the first place, async APIs are also incredibly hard to get right and have work all the time and have status and observability and all those pieces. Again, sponsored talk, so this is me shilling, but you should try out durable functions and try out that piece. I didn't write the async API part, I just wrote the programmability part. The not having to create an async API, not getting that wrong is so nice. I'm not just an evangelist here for this, even at Microsoft, I'm trying to convince as many teams as possible to move to using this framework rather than building their own, because it's very hard to get right. The functions team works very hard to make this really solid, and they've gotten it wrong because failures are going to happen, but when they find those bugs and they fix them in the framework, everybody benefits from that system. So definitely encourage you to look at something like functions or temporal or any of those things that are really kind of building these things to be hardened out, because it's a great way to build orchestrations. And with that, I think I've ended my shilling. If anyone has any questions, I can take questions because I think I have 3 minutes, but otherwise...